Welcome to Lecture 53, in which I'm going to take you deeper into the mechanics, if you will, or the nuts and bolts of quantum physics than I would in a normal course sort of just for non-scientists that had nothing quantitative in it. So we're going to go deeper into quantum physics here. We're going to look at quantum mechanics itself. We've already seen a history of quantum physics, or partial history of quantum physics, up through the Bohr atom. We've seen the essential ideas, in particular the idea of quantization, that energy comes in these discrete bundles called photons for light energy, the energies of vibrating atoms and molecules in the case of hot glowing objects. So we have the really basic ideas. But the question here is, what are the rules of quantum physics? What is there in quantum physics that's analogous to Newton's laws? That's the subject of this lecture. And how do we deal with the fact that classical determinism is gone, and yet quantum physics is still able to make at least some precise predictions? It just can't predict things like particle trajectories. And to get a little more specific, given that we understand there is this wave-particle duality applying both to light and matter, and we understand that if we can calculate what the wave looks like or figure out what the wave is going to do, then based on this probabilistic interpretation, we can go from there to find out what the particles are going to do and where we're going to find them. So what laws govern these waves, the quantum waves? Well, we know the answer already for light. The answer is Maxwell's equations. Maxwell's equations, in the classical sense, talk about light as an electromagnetic wave. When we do the quantum discussion of light, well, actually, there's a little more sophisticated mathematics that goes on, but a simple way to look at it is to say Maxwell's equations give us the waves, and looking at where the waves have large amplitudes, the electric and magnetic waves that Maxwell's equations say combine to make a light wave, looking at the electromagnetic waves and where they have large amplitudes is where we're going to find a photon. But what wave or what kind of wave is matter associated with, and what kind of laws govern the waves associated with matter? There's an equation that was developed in the 1920s by Erwin Schrödinger. It's the famous Schrödinger equation, and it is the equation that describes the matter waves. It's analogous to Maxwell's equations for electromagnetic waves. And we'll spend most of this lecture looking at the Schrödinger equation and then understanding how it gives rise to quantization and how it describes some particularly simple systems. This is the kind of material that would be covered in sort of the first real quantum mechanics chapter in an introductory physics text that was talking about quantum physics. So let's introduce first some basic ideas of quantum physics and get ourselves to the Schrödinger equation. How do we get to this equation? I'm not going to derive it rigorously, but I'm going to at least motivate it. I'm going to motivate it with some mathematics that again, goes deeper than I would normally go into if I were just talking to people who were non-scientists who didn't have any quantitative background or inclination. So what does the Schrödinger equation give us? It gives us a so-called wave function. The wave function is given the symbol psi, the Greek lowercase psi, for a given particle. It's a function of position, x, and I'm going to talk in one dimension now. Later in the lecture, we'll generalize to 3 dimensions, or 2, and time, t, although I'm going to talk only about the so-called time-independent Schrödinger equation, and I'm going to talk just about how the wave function depends on position. I won't go into how it depends on time, although it does. So if you square this wave function, I've emphasized this before, it's not quite the amplitude of the wave function that gives the probability of finding a particle at some position or other. It's the square of that amplitude, and that's going to become important. So the square of the wave function is important as a square because a wave can go positive and negative, but its square is always positive. And that square of the wave function, which is a function of position x, is going to give the probability of finding a particle at that position. We're going to express this in terms of mathematical operators acting on psi. Now, this is a new and fairly sophisticated idea that you probably didn't encounter in high school algebra. You may or may not have encountered it in high school calculus. Well, you did, but you didn't know it if you took calculus. I'm going to introduce some calculus terminology, but I don't want you to think I'm expecting you to know calculus. So I want to show some symbols, and things are going to get a little messy mathematically, but bear with me. The easiest operator to understand is the position operator, and the position operator is simply x, the variable representing position, and what the position operator does to act on this wave function psi is simply to multiply x by psi. Simple, ordinary, everyday multiplication. That's the position operator. The momentum operator is slightly more complicated. The momentum operator is proportional to the rate of change of the wave function with respect to x. And there are actually some classical physics analogies with this in more advanced treatments of classical mechanics, and I'm not going to go into those. But here's the momentum operator. P, which was just the symbol P in classical physics standing for momentum, becomes this operation multiplying by minus sign, I, the square root of -1, the imaginary unit, if you've heard of that. If you haven't heard of that, don't worry about it, because it's going to go away in a minute. Then h bar, which we're familiar with, Planck's constant divided by 2 pi. And then this symbol d by dx, d divided by dx, which is not a number. It's an operation. Those d's are the calculus limit of the deltas, the changes that we talked about a lot in introducing ideas like velocity and acceleration in classical physics. So minus I h bar d dx is what replaces momentum in the Schrödinger formulation of quantum physics. So the momentum operator, P, is minus I h bar d by dx. Now, what's the kinetic energy operator then? Well, we're going to do this in a Newtonian classical physics sense. The kinetic energy is a half mv squared. You can work that out. P is mv. Do a little algebra. That's p squared over 2m. Still classical. Now, to go quantum, we've got to replace p with its square. So I'm going to square that minus I h bar d dx. The square of a minus sign is plus. Minus 1 times minus 1. The square of I is -1. That's how it's defined. So we get a negative sign back. The square of h bar is h bar squared. We've got the 2m downstairs. And the square of the rate of change operation, d by dx, is taking the second rate of change, the rate of change of the rate of change. So that's what that d2 by dx squared is. And that's all going to operate on this psi function, this wave function. Then there's the potential energy that a particle might be moving through. It might be a particle attached to a spring. It might be a particle in the electrostatic potential of a proton. That would be the Schrödinger equation for the hydrogen atom, which we'll do in the next lecture. But U, the potential energy, is a function of position, so it operates in the same way position does. It's simply a multiplier. So the Schrödinger equation becomes basically the statement, and here's why I wanted to motivate all this and go through all that math. The Schrödinger equation is basically a statement of conservation of energy. It says kinetic energy plus potential energy equals total energy, except instead of being just the energies, it's the energy operators acting on the wave function. And that's equal to the total energy acting on, that is, multiplying the wave function. What does it look like? Putting it all together, it looks like this kinetic energy operator that I introduced with all these squared things, and we'll make sense of this in just a moment. The potential energy operator, U of x, a function of x, the function of position, acting on that psi function, just simply multiplying it. And that's E times that function. Oof! Now, if you had calculus or differential equations, we would proceed to solve this. We're not going to do that here. But I am going to motivate some solutions for it, including one that we'll get fairly rigorously. So there's the Schrödinger equation, the kinetic energy operator, the potential energy operator, and the total energy operator acting on the wave function psi. Woof! Let's see a very simple special case. The special case is the Schrödinger equation for a completely free particle. That is, one that's subject to no forces, one that ought to obey Newton's first law. In the classical sense, it ought to move at constant speed with no change in its motion because there are no forces acting on it. Well, here's the full Schrödinger equation. If there are no forces acting, it means there is no change in potential energy with position, so I might as well set the potential energy to 0. I can cross out that term, and I have a simpler equation that simply has the kinetic energy operator is equal to the total energy operator acting on that wave function. Because if a particle is free, it has no potential energy, there's no forces acting on it, and therefore the only kind of energy it has is kinetic. And now I'd like to reason by analogy. But first, let's restate this in English. I'm going to take that E times the wave function psi. I'm going to stick it on the other side of the equation with the minus sign. I'm going to pull the rest of the stuff to the right-hand side for reasons that will soon become obvious. So in English, it says minus the total energy times the wave function is these constants, h bar squared over 2m, times the rate of change of the rate of change of the wave function. Okay? Hang on, because now we're going to jump back to lecture 17 for a moment. In lecture 17, we studied the mass spring system. We put a mass on a spring. We knew that the spring produced a force that was minus kx, a force that was bigger if you stretched the string more, and it was a restoring force tending to pull the mass back to equilibrium. That's where the minus sign came from. And in English, we wrote that Newton's second law, F equals ma basically, with F here on the left-hand side, saying minus kx was m, the mass, times the rate of change of position. because acceleration is the rate of change of velocity. Velocity is the rate of change of position. So we've got rate of change of position here. That's how we treated the mass spring system. Now, we are not talking in this lecture about a mass spring system, although we will be a little bit later in a different context. We're talking about the Schrödinger equation for a free particle. But the point I want to make is these two statements in English translate into mathematical statements that are exactly analogous. We've got some kind of constant multiplying some kind of thing which is varying. In the case of the spring, it's the position x. In the case of the quantum case, Schrödinger's equation, it's the wave function psi. And that's equal to some constant times the rate of change of that thing. And consequently, we can immediately say, if we know the solution for the mass spring system from lecture 17, we can, by analogy, write down the same solution to the Schrödinger equation for a free particle. The solution we found in lecture 17 was that the position x of this mass on a spring was a sinusoidal function of time. It could have any arbitrary amplitude, and it could either be a cosine or a sine of some angular frequency times time, and the angular frequency turned out to be the square root of k, the spring constant, divided by m, the mass. That's all classical stuff from lecture 17. In analogy, we have x, the thing that's varying for the mass spring system. That becomes the wave function psi. T, the independent variable, the thing that things depend on for the mass spring system, that was the time. Here it's the position x. K becomes E. K, the spring constant, is like E in the Schrödinger equation. And the m, the mass in the mass spring system, becomes like h bar squared over 2m in our case. If you just simply look at those two English statements, you'll see those analogies. And consequently, we can immediately write the solution for the wave function. It's some amplitude, which we haven't determined yet, times the sine or the cosine of the square root, and putting in all those analogous things, of E over all that. And if I do a little algebra on that, it simplifies a sine or cosine square root of 2m times the energy times x over h bar. So, let's move on. Let us do now a very, very simple case, an actual calculation using the Schrödinger equation. And the reason I'm doing this, the reason it's so important, is because this is the simplest real quantum problem we can do. It's a standard textbook problem done in all textbooks. And importantly, it's going to show us where quantization comes from in the Schrödinger theory of quantum physics. So let's do this calculation. Very simple calculation. Again, it's a textbook thing, although in recent years it's become a real-world thing also because nanotechnologists are building structures called quantum dots for all kinds of purposes, electronics, all kinds of applications, and they are basically realizations of what used to be just an abstract textbook problem. So let's take a look at this textbook problem, this one problem in quantum physics that we can actually solve ourselves fairly easily. It's called the particle in a box. So we imagine a particle of mass m confined to some really rigid box of width L. The box is so rigid it can't escape. You could imagine a bowling ball bouncing back and forth between the walls of the room. Except this is a particle of rather small mass, and quantum effects are going to become important. So there's our physical picture, and I'm going to set up a coordinate system in which x equals 0 is one side of the box, and x equals L is the other side of the box. And we are going to try to find the wave functions and the possible energies for a particle in this box. Now, there's no forces on the particle within the box. The only time the particle gets forces is when it hits the walls. And we can easily handle those because in this case, the walls are perfectly rigid. We'll see something very interesting happens later if they aren't rigid. But if they're perfectly rigid, the particle simply can't ever get outside of the box. And so it experiences basically infinite forces that turn it right around. And so all we have to worry about is what the particle is doing when it's inside the box. And there it's a free particle. And we just worked out the Schrödinger solution for a free particle by analogy with lecture 17's mass on a spring. And we know that that wave function is some amplitude times the sine or the cosine of this quantity, constant 2me, where E is the particle's energy, its position x divided by h bar. By the way, I don't want to say a whole lot more about this A, and I'm not going to bother to solve for it, but I will tell you how a physicist would calculate that A. The physicist would say, if I have a particle, it's got to be somewhere. And so the physicist can sum mathematically the probabilities of finding the particle at all places that it could possibly be and set that sum to 1, and that determines the value of A. It's called the normalization constant, and I'm not going to have a whole lot more to say about it. We'll just assume we've got it figured out, and I'm just going to write it there as A. I'm much more interested in E. What are the possible energies for the particle? So there's no forces on the particle when it's in the box. except right at the edges where it just turns around, and we've got all that taken care of. We've got the rigidity of the box handled by saying the wave function has to be 0 right at the ends of the box because there's no chance that the particle will get outside the box. So that's our condition. It's a rigid box. There's no chance of the particle penetrating the walls. And that means that psi has to be 0. This wave function has to be 0 here at the left side of the box, and it has to be 0 here at the right side of the box. So our job is to find some function of position that has these properties. It's 0 at the left end of the box, it's 0 at the right end of the box, and furthermore, it has this mathematical form. How do we do that? Well, first of all, if psi has to be 0 at the left edge of the box, that rules out the cosine. Why? Because cosine of 0 is 1. We wouldn't get 0 at the left side of the box. You might say, well, isn't that kind of arbitrary? It is kind of arbitrary. It depends on where I chose my coordinate system. If I had put 0 in the middle and L over 2 on the left, L over 2 on the right, I would have used different functions. But choosing x equals 0 at the left edge and x equals L at the right edge dictates that we have to use the sine function. If we cross out the cosine function and adopt the sine function, then we are automatically satisfying that condition at the left edge of the box. At the right edge of the box, we've got to have the sine, that's all we're left with, of this complicated expression, be 0. How do we achieve that? Well, look at the sine function. It wiggles up and down, and it crosses 0. Starting at 0, it crosses 0 at pi, at 2 pi, at 3 pi, at 4 pi, at any integer multiple of pi. So this quantity, the argument of the sine function, has to be a multiple of pi, an integer multiple of pi. There it is, root 2me times L equals over h bar equals n pi, where n could be any integer. And that, if we solve for the energy, taking the squaring it and doing a little algebra, tells us the energies are n squared, pi squared, h bar squared over 2ml squared. And I can simplify that a little bit because h bar is h over 2 pi, and so that 2 pi squares gets it 4, that makes that an 8 downstairs and makes it a plain h upstairs. That's not so important, that's just numbers. But here's the big idea. We've got quantization. Out of Schrodinger's equation that itself doesn't say anything about quantization has come quantization, the quantization of the energy levels of the particle in the box. The wave functions, well, there they are. They become a sine n pi x over L if you work that out with those energies, and they are precisely the standing waves that can fit in that box, just like waves on a violin string determined by the two ends of the string being fixed. Same idea. Okay, there's our energies. They go up as n squared. I'm now labeling them E sub n. The nth energy level, there are our wave functions. I can simplify this by writing n squared E1, where E1 is the lowest energy level, h squared over 8ml squared. Here's an energy level diagram, just like the one we drew for the hydrogen atom before. Down at the bottom is E equals 0, but we can't have E equals 0. By the way, a consequence of the uncertainty principle. We have E1 as the minimum energy. The next energy is E2, which is 4 times E1, and then E3, which is 9 times E1, and so on. There's an energy level diagram showing the quantized energy levels for the particle in a box. We could have transitions among energy levels, and photons would come out with energies equal to those levels, and that's what happens in these quantum dot structures. There's a transition between 3 and 2, and more energy comes out. We could look at the wave functions. There's the lowest wave function, the ground state wave function, the lowest possible energy. Particle can't have 0 energy in this box. There's a 0-point energy. Next one, a full sine wave fitting in there. Next one, 3 sine waves fitting in there. Or 1.5 full sine waves, 3 half cycles fitting in there, and so on. Those are the wave functions. The probabilities are the squares of the wave functions. And notice what's happening. This behavior is extremely unclassical. If I had a ball bouncing back and forth between rigid walls, where would you be likely to find the ball? Anywhere in the box. It's moving with constant speed. There's no forces acting on it. And so it's just as likely to be anywhere in the box if you go to look for it. That's not what quantum physics says. It says in the ground state, it's very likely to be found near the middle of the box and less likely to be found by the edges. In the second state, it's likely to be found in the left half of the box, sort of in the middle of that, or in the right half of the box. You're never going to find it right in the middle, where the probability is 0, and so on. Whoa! That is very unclassical behavior at those low energy levels. On the other hand, you get up to E3, you get now 3 peaks of places where you might find it. And if you go even further, you will find that as you go to larger and larger quantum numbers, those numbers n that describe what state we're in, you begin to get more and more agreement with classical physics. And that That notion is called the correspondence principle. It's another principle that was formulated by Bohr, and it says quantum mechanics agrees with classical physics, but only in the limit of very large quantum numbers. When you get down toward quantum numbers 1, 2, 3, 10, you get much over 10, you begin to get agreement with the classical limit. And here's a way of seeing why that happens. Here are, again, the first 3 energy levels of the particle in the box, and now I'm going to break that diagram and put a much higher energy level, E20, and you'll notice it's wiggling like mad. Now, if I go to find out where the particle is when it's in the 20th energy state, I'm going to use some kind of instrument that has some kind of non-zero resolution. It measures, it can't get down to 0 size to determine exactly. It's going to determine the particle is somewhere within a range of positions. And when the wave function is wiggling very, very rapidly, the particle is going to see lots of those wiggles, and it's just going to get an average value, and it's going to be the same no matter where I put it. And I'm going to come to the conclusion that at high ends, high quantum states, I'm equally likely to find the particle pretty much anywhere in the box. And there's Bohr's correspondence principle, that quantum mechanics agrees with the classical limit in the extreme case of large quantum numbers. Okay, let's talk about a few more aspects of quantum physics, and then I'm going to look at a couple more quantum systems. First of all, an interesting thing about quantum physics, which is not true in classical physics, because waves can superpose. 2 waves can exist in the same place. We can have 2 waves that, in fact, add together to give a composite wave. And I'm going to start with a musical analogy. Here's a pure tone, which is described by a single sine wave. Here's another pure tone, which is described by another sine wave. And if I add them together, I get a composite wave which doesn't sound quite so pure and is a superposition of those 2 waves. Well, in quantum physics, I can do the same thing. I can have a quantum particle with that possible wave function, another possible wave function, and I can put the particle in a state where it is actually in a superposition state of 2 wave functions. And if I try to determine what the energy of that particle is, I prepare it in this superposition state, maybe 0.25 psi 1 plus 0.75 psi 2. By the way, those numbers are not quite right because it's the square of the amplitudes I should really be considering. And then I go to measure the state of that quantum particle. I will find some of the time that it's in state psi 1 and some of the time that it's in state psi 2. And given that there's more of psi 2 in the mixture, I will find it more likely to be in state psi 2 than in psi 1. But any time I try to measure its energy or any other quantity that has a definite value, I will get a definite value. What happens is the wave function essentially collapses and becomes one of those possible states that was there in the superposition. An example is a particle in a box. If it had a superposition of those states and then I measured it, I would get a definite value corresponding to one of the states in the superposition, and the probability of the outcome depends on the relative portion of that state. Wow. There is a lot of philosophy behind here. The whole idea of Schrodinger's cat that you may have heard of, a cat that's in a state of alive and dead, and what's the probability? The whole business of quantum entanglement that you may have heard of that I'm not going to have time to go into here, that's about superposition states and what happens when you measure the state of one particle in a pair that are entangled. Very fascinating ideas here, but we need to move on. Let me give you a few other examples of quantum systems. Here's a quantum harmonic oscillator. We've already looked at the particle in a box. It had those energy states. The harmonic oscillator has a potential energy function that is quadratic in position, as we saw when we stretched springs and found the work involved, and we can write that as a half m omega squared x squared, where omega is the angular frequency of that system. So there's a quadratic potential energy function. We can't do it here, but it's possible to solve mathematically the Schrodinger equation for that state, and what you get are, in fact, evenly spaced energy levels starting at a half hf, or a half h bar omega. Planck had it slightly wrong when he quantized the energy levels to be nhf of the vibrating atoms. It really started at a half HF and then went to 3 halves and 5 halves and 7 halves HFs. He missed that half. He missed the non-zero ground state lowest possible energy. But there it is in the quantum harmonic oscillator. And there are transitions among those states, and they all give equal energy photons, equal wavelength photons, because they're all transitions of magnitude HF. There is an interesting device. This has been very abstract, but here's a device that was Science Magazine's 2010 Breakthrough of the Year. It's the first quantum machine. It's a tiny little aluminum nitride prong. The the length of that thing in the horizontal direction in this picture is the width of a human hair. Now that's small, but it's not really, really small. It's not as small as we usually think of when we talk quantum physics. And yet when that thing is set vibrating, they were able to detect that the vibrations could occur only at certain frequencies, the quantized harmonic oscillator frequencies. Wow, a quantum machine, the first quantum machine just developed in 2010. Let's look a little bit more at this quantum harmonic oscillator. Here are the probabilities calculated from the wave functions. In the ground state, the lowest energy state, we have, again, this very non-classical behavior, because in a harmonic oscillator, it's going back and forth, and it's going slower at the extremes as the spring tries to pull it back. And so you'd expect it to be most likely to be found near the extremes because it spends more time there. In the ground state, you're most likely to find it in the middle, which is exactly the opposite of the classical case. On the other hand, you go up here to a higher state. Here's state 3, where it's beginning to get lots of wiggles, and you see the wiggles are bigger near the edges, and that's beginning to be the correspondence principle, showing that indeed we're more likely to find it near the extremes of its motion. So there's greater probability near the extremes. That's one feature of this I want to point out. Another is there's a slightly non-zero probability, as those wave functions have to go smoothly downward, both there and there, of finding the particle outside the region where it would be allowed classically. Energy conservation would not allow it to go outside the extent of that spring, depending on how much amplitude you give it. But here it can, and that leads to a phenomenon called quantum tunneling. Quantum tunneling represents the non-zero probability of finding a particle where classical energy conservation prohibits it. And in this diagram, you see the wave function of a particle on one side of a barrier, and the energy of that particle isn't enough for it to leap over that barrier. The potential energy of the barrier is too high. It doesn't have enough kinetic energy. Classical physics wouldn't let it do that. Quantum physics lets it tunnel through. And if the particle is very light and the barrier is very narrow, this tunneling phenomenon actually happens, and it's crucially important. We wouldn't be alive without it. The fusion of protons to make helium in the sun, which supplies the solar energy that keeps us on Earth alive, occurs because the protons are able to tunnel through the repulsive electrical barrier, Coulomb potential barrier. Radioactive decay occurs often because the radioactive particles can tunnel their way out of a nucleus. And today, we use tunneling in microscopes. The scanning tunneling microscope is a way of imaging individual atoms with a current of electrons that tunnels between a probe and the surface. And there's an example of a beautiful picture made by quantum tunneling microscopy. So those are some practical uses of quantum tunneling, this phenomenon that you can go in places, a quantum particle can get to places where energetically classical physics would prohibit it. Let me wrap up with just a few other comments about quantum physics. I've been talking in one dimension, but quantum physics particles live in 2 and 3 dimensions. We'll see that next lecture when we talk about the quantum description of the hydrogen atom. But here's an example in 2 dimensions, and you can fit wave functions in both dimensions. So you have 2 quantum numbers that describe how many waves there are. And in this particular diagram, in the y direction, you have half a wave, 0 at one end, 0 at the other, and you have a full wave in the x direction. And you can put together all kinds of combinations, quantum mechanics in multiple directions. And y is 1 and x is 2 in this case. Let me end with quantum mechanics and relativity. You may have heard that they're not compatible. It's true that quantum mechanics and general relativity have not been reconciled, but quantum mechanics and special relativity were reconciled decades ago by, among others, Richard Feynman. And what happens is, if you look at the Schrödinger equation, it was based on k equals a half mv squared, Newtonian kinetic energy. Dirac in 1928 said, look, what happens if we use the Einsteinian energy-mass-momentum relation that I introduced before? Well, I've got to take a square root. When you take a square root, there are 2 possible answers. And Dirac, instead of throwing out one of the answers, said, I think this means there are antiparticles, antimatter. And that was the theoretical discovery of antimatter. It came from the 2 roots of that equation. And Dirac developed a whole theory of the electron, a relativistic quantum theory of the electron with what's called the Dirac equation. And another thing that came out of that was that particles have to have an intrinsic angular momentum. It's called spin. Intrinsic, you can think of them. This is a bad way to think of it because you shouldn't think of them as little billiard balls. But if you did, they're kind of spinning, and that spin is intrinsic to them. It's what it means to be an electron, to have spin. And there are particles, most of the particles that make up matter are called fermions, and their spin is a half-integer multiple of h bar. Well, not quite. They come up with a number that is closely related to that, but they're called half-integer spin particles. They obey something called the exclusion principle, that 2 particles can't be in the same quantum state. And in the next lecture, we're going to see that's crucial to the existence even of chemical elements. That's the exclusion principle. All this follows from making quantum mechanics consistent with the principle of relativity. Then there are bosons, particles with integer spin, and they can be in the same state. Photons have integer spin. That's why I can make the intense beam of a laser. And that's why we've learned with certain atoms that are composite particles that are built up out of fermions but have integer spin in their composite state, we've developed something called the Bose-Einstein condensate in the last few decades, and that's a really hot issue in contemporary physics where a whole bunch of particles, atoms, collapse to form basically they all have a single wave function, and they're all moving basically together. Quantum mechanics and its reconciliation with relativity gives rise to some really crucial new phenomena that are important in understanding particularly atoms. Okay, let's wrap this one up. We've seen that the Schrödinger equation gives the solution for a particle's wave function, this psi function. We found that the psi function gives the probability of finding the particle. That probability is proportional to the square of that wave function. For confined particles, whether they're confined in our square box or whether they're confined in that parabolic potential energy curve of a quantum harmonic oscillator, we find that quantization arises naturally by the requirement that those waves fit in there. The correspondence principle tells us, look, quantum physics is very different from classical physics at low quantum numbers, but at large quantum numbers they begin to agree. There's non-classical behavior, though, deep down in the quantum realm at low quantum numbers, and there were several examples in our analysis of the quantum harmonic oscillator. And finally, relativity tells us there's got to be antimatter and there's got to be particle spins, fermions, and bosons.